things are pretty organized.
Really? Like there's something where they sort of always assume a matrix has an inverse or something.
Take the zero.
Yeah.
Yeah, it might be like if it's everything could be true.
Yeah, just a little bit of error in that. So I don't know. Doesn't make sense. I think like one day, my goal is to like study general relativity.
Yeah,
It's just like understand it from first principles. But I think it'll be like a long time.
that's hopefully my IT is 4 years.
Like I've like skipped a few of those books and it just seems like they just jump off into like coordinate systems and stuff like this without like explaining why anything is the way it is. Yeah. Huh? Geeks.
Oh, yes.
Like, what's your you?
I'm in the same office as you guys.
Yeah.
Oh, but you don't.
I never come because too many people all the time. I feel like
Although,
Who's your post professor?
7:30.
Oh.
And also wearing masks indoors is just so annoying.
That's true.
And we're all just concentrated in one group anyways, just come on. Figure it out.
the projectors. It's worth it. Don't be so bad.
The whole issue is here, black things.
Where we leave them, they
Not the calculations. There's only one result that they find.
consolidation of the system.
That's always different.
There always is. At least one says.
But the one is scared of it.
There always be one.
It's just that we need it's also, but it's not good.
They don't know how to improve it properly.
It's something and people in the
I was very good.
who's in mood? I could
It's expensive. Mine cost me 8.4.
yeah.
Euro, it is. Yeah, that is weird. I need to buy.
I got experience.
So we put it on
So much. So much.
Last we put it on.
Twice as much. You really often that.
It's a content.
Constant.
Yeah, everything is a constant crisis in this world.
I didn't complain.
Even that is a good intuition, guys. Not eating because it hurt. I thought it hurt. It was amazing. Especially how vegan. Yes. Awesome art for vegan.
It's going to have something.
That would be vegetarian.
No, it's not. Let him be happy.
I don't know why I think honey. I mean, it's not. No, you are not driving. You are driving. I mean, of course, that is. We can be clearly different.
You don't think any spiders in the home?
That even I don't have nice killing spiders. I wanted to do anything.
You don't?
I wanted to be open that I don't want it now.
Oh.
It's fine.
Sorry, everyone. Okay. No. One sec. No. What happened? No. Okay, so sorry for my delay. I'm gonna
recall what we have shown last time. One is the local min cut algorithm, and this algorithm says that if you are just given some seed node x and some parameters new, and then like this is for volume and this is for cut size, parameter k. Then basically we want to decide if there is some small cut like this, right? Where the volume in this cut is just at most new, and the number of edges going out of this is at most k. But we will not decide this exactly. What we will do is just either declare that no such cut exists, but otherwise, if we don't declare this, then we're gonna return a cut L of size at most k, but the volume can be like not at most k, not at most mu, but there's some gap of mu k here. The running time is nu k square. Okay, so like, do you recall roughly how did we do it? So we repeat k times, right? And we do some search, explore new k volume, and then we just sample among the edges that we have explored. With good probability, it will be outside the cut, and that's how we make progress. So that's the algorithm. But for today, just remember this subroutine. We're gonna use it. Okay. All right. Okay. So let's look at a simple application of this algorithm. The problem that we're gonna use the local min cut algorithm is just global min cut problem. So here you are given a directed graph, and you basically want to check if there is a cut such that the number of edges going out of a cut is at most k. Okay. So the graph, maybe it was strongly connected. Basically you ask how many can you delete k edges so that the graph is not strongly connected. That's the problem. Okay. And okay, there are some easy algorithm, but let's see how to solve it in near linear time when k is small. Okay. So first, there is an easy case. So here we allow randomization, right? An easy case is suppose that there is a cut, such cut S, such that it's quite balanced. So if this is a graph, then there is a cut S. And the volume on both sides is quite big. Okay. Then, just to recall you, volume here, you think of it as a number of edges incident to the set, right? So both direction you count. So it's just basically the number of edges from S to outside, and the number of edges from outside S to inside. You count all. Yeah. So the total volume is something like 2m. Okay. So if this is balanced like this, it's gonna be quite easy. How? Well, you can sample S and T, so that with probability proportion to its degree. Or in other words, you can imagine that you can sample two edges and take the endpoint of those edges. It's kind of the same thing. But if you sample S and T with probability proportion to its degree, then each node V is chosen with this, right? This probability. And because both S and V minus S have volume, something like M over K, then can you tell me how many times does it take so that you sample S inside S and T outside S? So if this is like a M over 2, how many times does it take to sample one node in S and one node outside S? Well, is it too easy? Can someone tell me? Well, it's going to be something like constant number in expectation, right? And suppose that we get a node. So why is that? Well, one sec. So maybe let me just go through it slowly. Suppose that like for each of the sample node S and T here, what I'm gonna do is just to compute ST min cut and check if ST min cut is less than K. And if it is the case, then we are done. Okay. And how long does it take to check this? You can use Ford Fulkerson, for example, and that takes MK times. Okay. And what I'm gonna repeatedly do this for K log N times. So the total time is gonna be this much. And why does it work? Well, so let's see. Suppose we have this promise, right? That there is a cut of size less than K, and both sides have volume at least this. Well, so then I claim that the above algorithm will just work, and the reason is that so the probability that S is inside S. So suppose that the volume of suppose that S is on the smaller side, so the volume of S is something like M over K, and the volume of the bigger side is gonna be something like at least M over 2, something like that, right? Because it is like 2M minus, like it's on the bigger side, so it's gonna be this. So the probability that you get S inside S is something like 1 over K, and T inside this is like a constant. So this is basically you multiply the two probability, you get this probability. And if this really happened, then you're done, because S is on one side, T is on one side, and this is a cut of size less than K. So you will find a cut. And the probability that so if we succeed, we are done. And how how can we fail too many times? That can happen only with this probability to the t. And this is small. Okay. So that is like an easy case. When the cut is quite balanced, and then you're good. Okay. Let's look at like another extreme case. Let me ask you, what if actually a cut S which have size at most k here? What if the volume of S here is a constant? What would you do? Can someone suggest an algorithm to me? If there exists such a cut. So how can we detect this cut very, very fast? Right. So we're gonna, like this kind of cut is exactly what local mean cut is for, right? So what you're gonna do, you can just simply, if it is extreme case like this, what you can do is just, for every node x, you just run local mean cut, like try every node, run local mean cut with from x with volume here, which is a constant, and k is like a cut size, and then if there exists such a cut with small volume, you're gonna find it, and the total time is going to be n times nu k square, which is something like nk square. Okay. And now let me ask you again. Let's say that it's not this extreme. Okay. But let's say that the volume is something like root m. So it's a bit bigger. S is a bit bigger. All right. Well, if you use this algorithm, it's gonna work. But now nu is something like root m. So it's gonna take longer time. It's not nonlinear, right? But we can make it better than this. Why? Because now we know that this set is a bit big, and so it's gonna be easy to guess something inside this set. Okay, so what if I say that I gonna like basically, let's say that I sample like root m edges and take, if I sample root m edges, then one of the edges will have endpoint inside S. And then if I say that, okay, let's take the seed to be the endpoint of this sample edge, then this algorithm gonna, like, this x is just endpoint of sample edges. Okay. Then now we're gonna, how much time we're gonna take? It's gonna be something like root m for the number of sample edges times nu times k square. So this is going to be m k square too. Now you get an idea, like if the volume is not root m but something else, let's say the volume is now nu. What you're gonna do is, how many edges you should sample? Something like m over nu times log n, just to make sure that with high probability one of the endpoints should be inside S, right? And then the running time is gonna be like this, and with some polylog. And this is how you get the running time of mk square. And you might wonder why do we why did I even mention the balance case from the beginning? Why can't we just use this strategy for all new? Because for any new here, you're gonna get mk square, right? Why did I even mention the balance case? And this is because actually the algorithm here works only when new is at most m over k. Actually, can you remark, do you recall? Actually, I didn't take care of this issue last time, but can you guess why, or can you tell me why actually there is this limitation? Very good. Yeah, very good. So exactly. So if you recall the algorithm, what we are doing is that we actually explore these many edges, right? And we say that if we get stuck, we return a cut. But if this is more than m, then it doesn't make sense anymore. You're gonna get stuck because you explore the whole graph anyway. So, right. Good. So that is the. So now that's why new need to set new only works when new is at most m over k. But if new is if the cut size, if the volume of S here is more than m over k, the balance case take care of it. Make sense? Or okay. All right. So that's the algorithm, actually, and here I just basically write down how to take care of all the level of new, but you got an idea already. Okay. So now let's recall what is isolating cut. Okay. Yes, please. Yeah. In the balance case, we use Ford-Fulkerson algorithm. That is, so you sample S and T, right? And you really just compute, check if the max flow between S and T is at most K or not. But to check that, you can run Ford-Fulkerson algorithm, which is really keep finding augmenting path for K times. So that algorithm takes just MK. Okay, good. More question about this? All right. Next is isolating cut. So let's recall the problem. Here, I say that let's say that A and B are vertex set, and A-B cut is just if this is A, this is B. A-B cut is just any cut that contains A but doesn't contain is disjoint from B. And AB min cut is such cut that is minimized, that is minimum, the size is minimized. And the problem of isolating cut is that you're given a graph together with a terminal set, and what you want to output is for every terminal you want to return SV, which is VT minus V min cut. So for every, if these are terminals, you want to find like 4 cuts such that each of them isolate this terminal from the rest in a minimum way. That's a problem. Okay, and last time we have seen how to do it in LogT MathFlow. I need to point out one of my error in class. So everything is correct actually, except that in class I mentioned this submodularity of a cut, right? That is, if you look at any subset of vertices and take delta as a cut size, then you have that the cut function satisfy this inequality, and this can be checked just by case analysis. I asked why this works only in unrelated graph, and actually it actually works in the related graph too. So thanks Tian for telling me this. And basically, if you just replace, like if you take the cut size function to be out cut, you count the total weight going out of a cut, you're gonna get this same inequality. And this can be checked just by case analysis too. You can check that. Okay. So that was my error, but it doesn't affect the correctness of everything because we were really talking about unrelated graph. However, even if this algorithm, isolating cut algorithm, it works correctly in unrelated graph, the whole thing still doesn't work in the related graph. And and the reason is actually something like this. So if I define, if I define S star V, so in previous class we define S star V, right, to be inclusion-wise minimal min cut. We can define the same thing in the related graph, which is given a node V. Now we really look at the related, like out cut, like a cut such that the size of cut from V to outside, the cut, like you take S and the out cut is minimized, but this cut should isolate V from the rest. Okay. Here you can talk about inclusion-wise minimal cut of this type too, right? And which I mean that, like if there is any other cut SV that contain, such that SV contain S and this is minimized, then this is like it's inclusion-wise minimal, so it is contains inside S. We can prove that this exists too, no problem. And the reason is just using the submodularity of delta out. Okay. However, the problem was that now recall the algorithm, right? You have a graph and some terminal set like this, V1, V2, V3, V4. And what we do is kind of we try to divide like terminal set into two sides, and we compute min cut. And now, what we did, like we call one side is red, one side is blue, and we compute min cut. Now, which direction of min cut we should compute? If we compute min cut, like that is going out from R to B, the min cut might look like this. This is the minimum cut, minimum out cut from R to B. However, if you compute BR cut, the cut such that this is minimum, it can be different cut, totally different cut. And the important thing is that this thing can overlap really a lot. Okay. So now, this thing and this thing can overlap a lot. And this is a problem. So in the underrated case, we know that they are the same cut. And what we can do is just, we can really define, like when we compute C1, C2, and we delete this thing from the graph, then you really have the partition of nodes. Like this cut in underrated case really partition a graph into parts. Now, it's not clear what do you do here. You have two cuts, which are not the same, and if you only take one of them, it's gonna be wrong. Like, and if you take both of them, like, it will be explosion because they overlap too much. Exactly. So you can think more about this, but try to convince yourself that it doesn't really work. Okay. But now let's try to use it. Let's try to given isolating cut algorithm. Let's try to use it. Yes. Yeah. If we right. So if we use, so okay. Let me tell you about one claim that is actually gonna be true. That is, suppose that you have one terminal V here, right? And if this is SV star, like it's minimal outcut from V. And here, if I like now consider like when I compute a cut that separate two sides of terminals, if I take cut in this direction, it's a min cut from left to right. We're gonna actually can show that this is going to be inside left. This is gonna be the same proof really as in underrated case. Okay, so it cannot be the case that S looks like this. No. Now, so you know that when you divide terminal into two sides, if you compute it in this direction, it's gonna be good for all of the terminal on the left. Okay, but it's not like useful for terminal on the right, because terminal on the right, the SUV here, this thing can intersect, right? So so this is not good, but okay. But now, yeah, So exactly. So if we like define, like if you do this thing and do this, and you define this part to be UV, like in previous class, the total volume of UV is not going to be linear, like in previous case in the dotted graph. Of UV can be like mn. Like each of them can be very big, as big as n, and there are n of them. Question?
Why can we?
Because so each of the volume of UV actually can, if you take like volume UV in the directed case to be like you, for each of the V here you take the intersection of our cut. This thing can still be very big, can be as big as n, and each of them can like, and then for if you take like UV2, this is V2, UV2 can be like overlapping with UV1 really a lot, like so each of them can be big, as big as the whole graph. Yeah. Okay. Now I'm gonna tell you about application of isolating cut. So it turns out that this is super powerful. So let's look at this problem where you have undirected weighted graph and some terminal set T. Okay. So you have a graph, some terminals. And now I just want to find some cut that separates some pair of terminal. The cut might be like this. So as long as it separates some pair of terminal, you're good. That's what I want. And I want such cut that is minimized. The cut size is minimized. So people call it T-Steiner min cut. But you can see that this problem actually is a generalization of both global min cut and ST min cut. And the reason is that if T is everything, then you really just ask for any cut of minimum size. Right? It's global min cut problem. And if T is just have two vertices S and T, this is exactly ST min cut problem. Okay. And it turns out that just until very recently, the only algorithm which is known is just to compute T minus 1 minimax flow. And how to do that? Why does it solve this? Well, you just choose arbitrary node S in the terminal, and you compute min cut from S to every other terminal. It's gonna be like, it's gonna like, because the optimal cut gonna separate S from some terminal, so one of the min cut, one of the max flow will work. Okay, so that takes a lot of max flow. And now we're gonna see that you can just take something like polylog T. Polylog T isolating cut, and each isolating cut takes polylog max flow. So at the end, it's gonna be polylog. Okay. So let's see one simple, the idea is super simple actually. So suppose, for example, that S star is our T-Steiner mean cut, the cut that we want to find. But suppose for some reason, this S star, it really isolates some, it contains only one terminal, V. So it's isolate V from the rest of the terminal. Well, in this case, we can if we just call one isolating cut, we are done. Because isolating cut actually gonna return you a minimum cut that's separate. That's isolate each of the terminal, but the Steiner mean cut is one of them. So just one call to isolating cut, you are done. Okay. Now, it might not be the case that your Steiner mean cut really isolate one terminal. Your Steiner mean cut might contain something like 2 to the k terminals. In this case, isolating cut is not good, right? Because it can be the case that, let's say this is the S star, and the cut may be of size 10, but the isolating cut for V maybe it's gonna be of size maybe let me be so the graph may look like this basically. V2, V3, V4, and this is 1 and this is 100, right? If you need to isolate V2, you're gonna need to pay 100. It's not 1. So isolating cut might not be a minimum Steiner cut. Okay, so here isolating cut is not useful, but it's actually easy to make it useful. And the reason is that what you can do is you can subsample your terminal set. Your terminal set is T. Let's subsample and T, subsample each node in T with probability 1/2 to the k, and call this set T prime. And now just do this. Then you know that the probability that now S star and T prime really intersect at one node exactly. This is gonna be constant, right? But and if you know that the T prime intersect S star is just of size 1, it really isolates one node in T prime. What do? You can just call isolating cut with respect to T prime, and you're done. Okay. So now that's it. Now what you can do is that if you want to boost the probability, you can try to sample T prime log independent. You can try log n independent sample of T prime. Then one of them gonna intersect S star at one node with high probability, and you compute isolating cut from that T prime. Okay, so you're done now if you know the cut size, how much S star intersect with terminals. But if you don't know the size here, now you can just try for all log n many level of the size to the k here. So that's it. Then there are log n many level. For each level, you try log n many independent sample. One of them gonna intersect S star at one node. and that for each of these T prime you call isolating cut. Each isolating cut takes log n max flow. So there are log square log isolating cut. In total, there are log cube max flow. So that solved the problem. Okay. So, question about this? Okay. And now, there are many other things that you can solve using local cut and isolating cut. And we're gonna discuss this in the exercise session. For example, if you know that the graph is an expander, then you can check the same problem if the graph is k connected or not in something like m poly k time. But now it's deterministic. Actually, let's try to do this for now. Actually, yeah. So, and the other two I'm gonna do it in the exercise session. But here, so this is like I really asking about global mean cut problem, right? Can you have a graph? Can you delete k edges so that the graph is disconnected? But suppose now I have a promise that the graph is an expander. So we know that randomized algorithm you can do it in mk square. Now we're gonna do it deterministically. So what do we know about expander? So suppose right that there is a cut of size k in expander such that you disconnect the rest. What do you know about the volume here? It's at most k times phi. All right. But if we know this, then what you do? Yeah, you call local mean cut from every node. So from every node you call local mean cut, and the local mean cut. So just for all x, just call local x with new, which is k over phi, and this is k. And then the total time is going to be n times this thing, which is new, times k squared. And this is like so very simple. Oh, you're right. Okay, suppose that I forget to there is a local mean cut which is deterministic too, but I forget to. All right, yeah. Good point. Sorry about this. Maybe how to make it deterministic I put in the homework maybe, but yeah, you can make it deterministic. All right. But actually, yeah, sorry about this. The deterministic algorithm actually, so randomized, it takes this time. The best deterministic algorithm still takes something like this time. So it's still local, but it's not linear in volume. and maybe I will ask you about maybe it's, yeah, just know that it exists for now. Yeah. And okay, there are many more applications. Actually, anyway, let me talk about this too. If a graph is an expander, now you can actually, like, what we want to do is now we want to do something like single source min cut. You have S, and you want to list all of the node T such that the min cut from S to T is quite small. And by small, I mean like, think of alpha as maybe 100. So min cut is less than alpha times mean degree of a graph. Okay. So what you can see from here is that no, alpha is something like 100. Like alpha is some big number, big constant, say. Like alpha is 100. Okay. So the idea is gonna be simple too. The reason is that suppose that min cut from S to T is as small as this, like smaller than this threshold. So let's say T is here, and min cut is less than alpha times D min. So let's say this is ST. How many nodes ST can have? So what do we know? We know that the weight from ST to outside, like the weight of the cut here, this is at least 5 times the volume of ST, right? And this is also at least ST times D min. Right? However, this is at most alpha times D min. So ST gonna be small. It's gonna be something like alpha over 5. So you know that for any T, if the min cut is small, then the number of nodes that it contains is going to be small too. Okay. So now, what if I say that, let's say that I define a terminal set. Okay. Suppose somehow that terminal set that I define contain, let's say I define terminal set, and the terminal set contain S, and if it contains only T and nothing else in this cut, then the isolating cut algorithm, what would it do? Well, it would return you a min cut that separate T from S, right? Make sense or not? If, yeah. So suppose you can can guess a terminal set T, and T contains S, and T intersect ST is just T. Then isolating cut with respect to T gonna return you some min will return some min cut, some ST. So this is just ST min cut. ST here is just some ST min cut that we bound the number of nodes, right? And so we know that the excess ST min cuts that have small number of nodes. But if T actually it doesn't really contain any node inside ST except T itself, then you know that then like ST is T isolating cut, like minimum T isolating cut with respect to T. And so if you call isolating cut, you're done. Okay. All right. So this is what we know, that if we can guess somehow can guess this terminal, then you are done for T. All right. How would you guess this T? Can you tell me?
The size of ST is bounded, so we randomly pick then only one we can get a probability with some, at least some, that only one.
Yeah, exactly. So what you can do is that to guess T, can do one thing is that you always pick S in T. Is a source. You always put it there. But for other vertices, include each node in T with probability something like this thing, inverse. So phi over alpha. And if you define it like this, then you're gonna have that with probability, the probability that this event happened, this and T intersect ST is just T. This is gonna be something like, so let's call this thing P. It's going to be something like P. Why? Because you're gonna pick T with probability P, but you wouldn't pick the rest with probability constant, right? So this is like the good event for T happen with this probability. And so you can try this experiment something like 1 over P times, then one of the experiment gonna be good for T. And for each experiment, you just call isolating cut. So that's why in total, you're gonna take something like 1 over p times log n maybe isolating cut, which in total is gonna be this minimax flow. Make sense? Okay. Okay, good. So there are so many other things for isolating cut, but I'm gonna, like these two are just two Q techniques, which is not so related to expander. This is just like something that I include into the class. But now let me tell you about something else now. So this is called cut matching game, and this is one of the most powerful technique, which I don't see people teach it, but I really think this is like really important that it should be in some class at some point. So now we're gonna see. So for today, I will just introduce the game, the cut matching game to you. And next time, we're gonna see the algorithm for it. But, all right. So a cut matching game, there are really like two parts. One is, which is about this. One is about the game itself. And one is about how to use the game. So how to use the game will be like maybe next week or something. But this is about the game itself. And for the game itself, you should think about it as a way, an algorithmic way to construct an expander. So we have seen from the first class that I mentioned several ways to construct an expander with low degree. Some is like explicit construction like hypercube or something based on algebra. You see in the homework that random graph would work too. But now, think of it as now there is like some interaction going on, and that is we want to say that we can force some adversary to construct an expander for you. It's like the way to construct an expander under adversarial setting. Yeah. And the game is like this. There are two players. One is called cut and one is called matching player. And initially, there are just empty graph. G0 have n nodes, but no edge. Okay. And now we're gonna proceed in rounds. For each round I, is this gonna happen? The first thing is that the cut player gonna do something first. The cut player will choose some cut AI, BI. Might not be like exactly equal. It can be like AI, BI like this. So let's assume AI is on the smaller side. And now what matching player gonna do? Now matching player must add a matching. And if AI is on the smaller side, the size of the matching need to be as big as AI. So if there are like 10 nodes here and 20 node here. Then you need to add like a matching of size 10. Like it must match every node in AI. So if AI and BI are equal exactly, then the matching is going to be perfect. Okay. All right. And then once a matching player chooses a matching, then you add the matching into your graph. So union it into your graph. So the graph keep, like you keep inserting matching into your graph. And keep doing this in rounds. So the last graph is just a union of all matching. So whenever the last graph becomes an expander, the game will stop. And you return the graph G as your graph. G is just Gi last. Another goal of each player is this. The cut player, he wants to construct an expander in fewest number of rounds. The cut player wants to get an expander. So what he needs to do is like he needs to choose clever cuts somehow that kind of force the machine to add edges so that at the end the graph gonna be an expander. And for matching player, he doesn't want to get an expander. So think of it as he really just adds some arbitrary or adversarial matching. So he need to add a matching that cross this cut. That's his requirement. But he might try to like add it in a way that is not, the graph is not really it doesn't have the graph to be an expander. He wants to delay this process. Okay. And yeah.
That you only can delay and you can't
Say it again.
so the matching player, you can only delay the happening of the expander, but you can't find a strategy where the graph doesn't become.
Yeah, we're gonna prove that no matter what matching player do, there is a clever enough strategy for cut player such that lock in rounds, you're done after lock in rounds. Right, so think of yourself as a cut player today. You're gonna come up with a clever strategy for cut player such that no matter what matching player is, after lock in round, you're done. Okay. So in later part of the lecture, like next week or something, we're gonna assume actually today you think of yourself as a cut player. Later you will think of yourself as a matching player, and you assume that there is some very strong cut player already, and you're gonna think okay, even if you choose some arbitrary matching in each round, the cut player gonna construct matching, gonna construct expander eventually. And this view of doing things against each other gonna have a lot of application, but this is for later. Okay. Okay, so there is a very natural heuristic for this game actually. So how would you choose a card, right? One thing is that it's very natural that you should choose a card which is quite balanced. And the reason is if you just choose a card such that it contains, let's say, one node, yeah, then the matching player is just gonna add one edge. It doesn't really help much. So if you choose it balanced in the balanced way, the matching player add n edges. So that's good. And now given that your goal is to get an expander, so if the graph is not an expander yet, it means that there is a sparse cut. So let's say there is a sparse cut. And so it's quite natural that A and B should be a sparse cut. Like the cut here should, if it is sparse, like if it is this cut basically, then you know that after this round, once if you choose a cut to be this, then the machine gonna fix this cut because it need to add matching from S to outside S. So it's gonna fix this sparsity of this cut. And actually, maybe even if AB is not exactly the cut, but if A contains this cut, it should be fine too, right? Because if A contains this cut, this sparse cut, then the machine gonna add an edge from S to even outside, like even further outside. So it's gonna still fix this sparse cut to be not sparse anymore.
But what if A minus S is the place where you are adding it this wall?
Sorry, can you say again?
A minus S, there is some place, there are some nodes in A minus S.
Uh-huh.
And from there, if we add the cut, it just then it doesn't help our sparse.
Yeah, but like we know that every node in A, you will get some edge going out. Yeah. So you have this thing too, but everything in S, you still add edge going out. Okay, so even if A is not itself is not sparse cut, if it contains sparse cut, it's still fine too. So this is like just so natural heuristic that you should aim for. And it turns out that this is like enough. However, to formalize this is non-trivial. But I'm gonna tell you like high-level goal of the analysis. And this kind of, you see that this kind of links a lot of things, random walk, flow, cuts, and all together. Okay, so let's consider this random walk process based on the matching. So imagine that you start from one vertex, V0, okay? And in route I, so let's say that you at V0. And so in route I, what you're gonna do is that you're just gonna stay at the same place with probability half. But otherwise, with other half, you're gonna move to another node using a matching edge. So that is, if this node in this round, M1, is matched to some other nodes, V1, then you stay at the same place with probability half, or you just jump to the another guy that you matched with probability half. If you are not matched, you just stay. Okay. If you are not matched in this round, you just stay at your place. Okay. And we can talk about the probability that a random walk starts at U and it ends at V after I rounds. This I denoted by PIUV. Okay. So the goal was like, there will be two algorithms actually that I'm gonna present, but both of the algorithms will have the same kind of goal. That is, we're gonna actually show that maybe after this round, all log square, like one takes log square. We're gonna show that after these many rounds, then the probability that you start at U and end at V is at least 1 over 2n. So know that if this is like 1 over n for all nodes UV, then it means that from U, you really uniformly go to each node in a random way uniformly. Now I'm gonna just need that, okay, no node get very small probability. Okay, so still quite close to uniform. So why do we look at this goal? Okay. So why this goal actually makes sense is that you will see that if this is true, then you can embed a clique. Like you can embed a clique into G. By a clique, I mean like K, where K is like one product graph. So it's a graph where each edge is of weight 1 over n. You can embed this clique as a scaling to G. And if you can do that, it means that G is an expander. Right. However, I'm out of time. So we're gonna actually stop for now because I will need like a large chunk of things to really explain this cut matching game to you, right? But okay, so let me see if there is something I should talk about before. Yeah, so I think I guess today is that's it for today, and we talk about cut matching game more on Thursday.
There is no one describing for the
Should we talk?
Yeah, in your professor.
Yeah, let's do that.
Yeah, I already asked Hanji.
Okay, then I will meet you there in like 5 minutes or something.
Okay.
I talk to other students for just a bit.
Okay. Sure.